Today's video is about water potential, which is a way to measure if water is going to move and in what direction it's going to move. So I want you to think about pure water. If you have pure water, it has a water potential of 0. So the sign for water potential is a psi. So if you have pure water, water potential is 0. And water always moves from areas of high to low concentration. So I want to compare two different solutions. So let's see here. We've got a beaker of water, and we have a cell. And so here, this solution has a water potential of 0. And that's because it's just pure distilled water. There are definitely solutes within a cell, so the water potential inside the cell is going to be lower. So let's say this is -2. What would happen? So obviously, if you put a cell in dissolved water, distilled water, sorry, water's going to move in. So that one was a pretty easy one to predict. And over here, this water is in an area of high concentration, and then here the water was in an area of lower concentration. So of course, water moves from high to low. All right. Now, how to calculate. So, water potential is equal to the solute potential plus the pressure potential. So, pressure is something that exists in cells only. So, if we talk about a beaker, we're not going to be adding in pressure because atmospheric pressure would act on a beaker, but it would act on everything equally. So it sort of negates the need to add that part in. So just if you have a cell, then you're going to have to add the pressure in. And the pressure is going to be turgor pressure. So turgor pressure is if I have a cell, here's my plant, there's my cell wall, and here, let me use a different color. Here is my cell membrane. The turgor pressure is the amount of pressure that the membrane is exerting against the cell wall. So if you think about that for a minute, if you have water coming into the cell, the turgor pressure is going to go up. There's going to be more pressure pressing against that cell wall. All right, let's talk about the solute potential. So solute potential is equal to negative ICRT. So it's always negative, and that's because it's always going to be a lower water potential than pure water. So anytime you add solutes, your water potential is going to go lower and lower and lower. All right, C. Oh, I'm sorry. Got to start with I here. I is an ionization constant. And for all the ones that we do in AP Bio, we're going to use sucrose, and the value is going to be 1.0. Oh, let me also tell you, this is all on your reference table. So when you need this, you just go right to the formula sheet, and all the values are there. All right, C is the concentration, and it's a molar value. R is a pressure constant, and it's always 0.0831. Again, one of those numbers that you will end up memorizing. You don't have to because it's on your reference sheet, but you're going to use it so many times you're going to get used to it. And then T is the temperature. And the temperature has to be in K, so that means you have to take your Celsius temperature and add 273. All right, so let's do an example. Really will help you get this going here. So first, let's do just a solution. All right, so let's say this solution is a 1.2 molar sucrose solution. So there's sugar in here. All right, and let's say we're at 25 degrees Celsius. So we have to do our calculation. Whoops, not sure what's happening there. All right, this is equal to negative ICRT. So I've got negative 1.0. My C is 1.2. My R is 0.0831. And my T, 273, plus this would be 298. All right, let me grab my calculator here. All right, so now I want to multiply these together. All right, and if you just did that at the same time as me, you would get negative 29.7, and then the units are bars. All right, and if you had to do sig figs, which I know we don't really do it so much in AP Bio, the chemistry person in me always wants to go to sig figs. There's 2 sig figs over here. We got 2 sig figs right here. That has 3 sig figs in it. This one's got 3 sig figs in it. So I'd have to go to 2 sig figs, which would mean my actual value would be negative 30 bars. That would be my answer. And I'd have to put a decimal there to show that it's 2 sig figs. All right, so that's how you solve it if you have just a solution. But of course, we're going to have more than just a solution. Very often, we are going to have a solution, and we're going to have a cell inside, because this is biology, and we want to talk about how cells are going to behave. And I draw it like a regular cell, but you got to realize this is probably going to be a plant cell. So let me go give it a cell wall. All right, so I have this cell, and you have to be given quite a bit of information to do this. So first of all, they would have to tell you the pressure, the turgor pressure. So let's say the turgor pressure is equal to 4.5 bars. Now, a pressure is pushing on the cell, so that's a positive value. All right, and then I would need to know the sucrose concentration inside the cell. So the cell has a 0.2 molar sucrose concentration. Then I would need to know what the beaker had. So the beaker has a let's say, let's go with a 0.1 molar sucrose solution. And let's say it's 25 degrees Celsius. All right. Now, what I advise you to do is to make a little T-chart. And you're going to have to do the solution, and you're going to have to do the cell. When you do the solution, all you're figuring out is the solute. Okay, so negative ICRT. Because, again, there's no pressure. So when I do this, I've got negative 1.0. Oops. Oops. All right, 1.0. My C for my solution was 0.1. My R is 0.0831. And my temperature, 25 plus 273, is 298. Oops. All right, and I'm going to multiply these together. So 298 times 0.0831 times 0.1 times 1. Okay, that would give me, I'm going to extend this out a little longer. This is going to be negative 2.5. All right, and then for the cell, I'm going to have to do a little bit more work. So I'm going to do this in another color so that you see the difference. This is going to be equal to this plus this. So first, let me solve the solute concentration. So negative 1.0. The concentration in the cell is 0.2 times 0.0831 times 298. All right, so that would be 4.95 with a negative value there. All right. Now what I would need to do is I would need to say this is equal to negative 4.95 plus my pressure. So I go back up and I see what the pressure was, and it was 4.5. So negative 4.95 plus 4.5 is going to be equal to negative 0.45. All right. So what I have is, I'm going to just draw my solution and my cell again. So out here, it's negative 2.5. And inside my cell, it's negative 0.45. So higher concentration would be inside the cell and lower would be outside the cell. And so sometimes you really got to think about that. I think it's helpful to think like a thermometer. If this is my thermometer, here's 0, negative 0.45 would be here, and negative 2.5 would be down here. So this is higher and this is lower. Water always moves from an area of high water potential to an area of lower water potential. So water would move out of the cell. All right, so if I go back to the beginning, I really wouldn't have predicted that. There was a higher sucrose concentration inside the cell, 0.2, than there was outside the cell. Sorry, it's making these goofy lines there. But you see what I'm trying to show. 0.2 is what there was inside of the cell, and 0.1 is what there was outside of the cell. So if I just thought about hypertonic and hypotonic solutions, I would have expected water to go into the cell. But this is where biology is so important. The pressure within that cell wall was exerting so much that actually water is going to push out of the cell. All right, so that's why we have to look at it this way and do our calculations and figure out our water potential. So I have one more diagram that I wanted to show you because I think it's super helpful to see. An area where water potential is going to be really important, obviously, is if we look at plants, and especially big, tall trees. So water in the soil is going to have the highest water potential. It's going to be the closest you can get to pure water. So here we have soil, and the water in the soil is negative 0.3. And then as you start moving up this plant, it keeps going from an area of high to low to lower to lower, and eventually what happens is the water is going to go into the air. So the air has to have the lowest water potential compared to each of these. So let's just go up and look at the values. In the trunk, we've got the xylem, which are the cells that move the water, negative 0.6. And then moving up a little higher, negative 0.8. And then in the leaves, negative 1.0. And then in the air spaces, so now we're talking about the stomates and the air spaces, like it's called spongy mesophyll. It's part of the leaf that you're going to learn about later. It's negative 7. And then outside in the air, negative 100. And this next slide, I wanted to show you the air is not all the same. So I want you to think about us in the summer. So let's write Rochester right here. We have very humid summers. So let's say it's 90% humidity. That's when you walk outside in July, and if you feel like you're soaking wet and sweaty and you haven't even done anything, that's because there's so much water in the air. So when there's a lot of water in the air, the water potential tends to be a pretty high value relatively. So it's much lower than any part inside of a plant, but it's higher than you would expect. And when you think of a place like Arizona, I don't know if you've been to Arizona, but But Arizona is a place where the air is so dry. You're outside and you're exercising like crazy. You can be literally climbing mountains and you don't feel sweaty. And the reason why is this. The water potential of the air is so low that sweat evaporates immediately off of your skin. So when there is extremely low water potential in an area, the plants really have to have special adaptations so they don't lose all their water. Plants are going to lose a lot more water in an area like Arizona than they are in a place like Rochester, which is why we have such abundant plant growth here in Rochester versus in Arizona, there's just so many rocks. So I want you to go through and I want you to do a bunch of practice problems. I have another video that is really just a tutorial of problems if you want to go through more step by step with me. Thank you.